Hi guys, and welcome to AtCoder beginner contest number 250, which is a lot. It is 250,000. So it's really amazing to see how far AtCoder come in the last 10 years, and I hope one day we will get to AtCoder beginner contest number 1000, but that day is not gonna be soon. I don't think. So yeah. In contest, I was able to solve problems A through F. Both G and H, or X as they call it, were solvable today. Unfortunately, I missed both of them, but after the contest completed, I was able to solve both of them. So today we are going to look at all the problems. Let's start with problem A. Adjacent squares. In this problem, we had a grid with H horizontal rows and W vertical columns. We were given a square RC, at row R in column C, and we needed to count the number of squares adjacent by side to this square. So the way I did it was the following. A square RC has a neighbor to the left, or to the left, if and only if it is not in the first column. A square RC has a neighbor to the right, if and only if it is not in the last column. And the same goes for neighbors above and below. So we can just, each of these conditions is 0 or 1, depending on whether or not the corresponding neighbor is indeed correct, a valid cell. So yeah, that's how I did problem A. In problem B, enlarged checkerboard, you were given integers n, a, and b up to 10, and you needed to print a checkerboard with dots denoting white and dashes or hashes denoting black. So the board was n times n, but each cell was a times b. So you can see here each cell is, each color occupies like 3 by 2 rectangle. So this is still obviously just an exercise. The way I did it, I iterated over all coordinates. So row goes up to n times a and column goes up to n times b. And then you can restore the coordinates in the original n times n board by dividing by a and b respectively. And then a simple way to tell if given cell is white or black is you take sum of its coordinates and you check if it's even. If it's even, then cell is white. If it's odd, then cell is black. That's how to solve this problem. Problem C, adjacent swaps, we had n balls in a row and we wanted to perform Q operations in which we swapped ball with number xi with either the next ball to the right, or if no such ball existed, to the right. So if this number was rightmost, then we swapped with the next left ball. So the way I did it, obviously, it's not, we want to have a quick way of knowing where is each number. For that matter, we will maintain inverse permutation, and by the way, the original sequence of balls was a permutation to guarantee that like there is a unique ball with integer xi written on it. So I say we are going to maintain our permutation and inverse permutation. And given that piece of information, inverse permutation, we can quickly find position, then we can find the position with which we are going to swap. So like if it is last, then we swap with previous, otherwise we swap with next. Then we can find actual value with which we are going to swap. Now we have to update both permutation and inverse permutation, and in the end we just print the answer. So maintaining inverse permutation, or in general any sort of information about positions of numbers, is generally useful. in case you want to quickly find where is the given value and apply some local operation to it. For example, swapping with the next or previous is a local operation. Something more complicated may not be a local operation. That's problem C. Problem D. We wanted to count integers that are less than or equal to n and can be expressed as p times q cubed, where p and q are primes with p less than q. So these numbers were called 250 like because 250 is obviously such a number with p equal 2 and q equal 5. So it's like 2 times 5 cubed or 2 times 125, which is 250. So for this problem, you can notice several things. First of all, you can number q, prime number q, is at most a cubic root of n, because obviously n is greater than or equal to q cubed times something. So q is relatively small, and then p is less than equal to q, so p is also small. Namely, both prime numbers are at most 1 million. So it's very natural to compute prime sieve up to 1 million. After which, another idea is to count such numbers p times q cubed grouped by q, because if we do it, then we know, well, we have two bounds on the value of p. First of all, it is at most q minus 1, and second, it is at most n over q cubed. So given q, we can tell what is the maximum possible p. And once we know maximum possible p, all the prime numbers up to this value, they are possible candidates. So we want a way to tell quickly how many prime numbers are at most something. Obviously, once we computed prime sieve, we can just compute prefix sums to tell how many numbers in a range are prime. So that's this problem. And technique of, like, whenever you want to count number of tuples, and in this problem we wanted to count essential number of tuples or pairs pq, it is always useful to think, can I group the tuples based on like first element on p? Well, not like, it doesn't sound like it, right? Because like, well, you can say that p is at most, actually you can group over p as well in this problem, because p is at most n to the power of 1/4. So maybe you can do even better sieve, but I don't know. But to me it was more straightforward to group over q, because then counting prime numbers is a bit easier than counting cubes of prime numbers. But in general, the idea is, if you want to count pairs, tuples, whatever objects consisting of several elements, that is not arrays, not subsequences, not substrings. You want to count, all substrings can be represented as two numbers, but if you have like fixed number of things in a object that you want to count, always try to group over one of them. It usually helps. In the next problem E, we had two sequences A and B of length n both, and several queries of the form: consider prefix of A of length xi and prefix of B of length yi, and tell if the corresponding sets, so like excluding duplicates, are equal or not. So there are three solutions to this problem, at least three solutions that I know of. The intended solution works as follows. First of all, let's pre-compute for each prefix of A and B what is the size of set that is formed by the corresponding prefix. Because if for a given query, if sizes of sets are not equal, then obviously sets themselves are not equal. You can think of set size as the simplest possible hash. So you want to quickly compare sets, it makes sense that you want some sort of a hash function that discards majority of information about a set, but still can sometimes, preferably most of the time, tell the difference. So the most simple function that clearly does not work in all cases is the size of the set. But still, if sizes are different, then we can immediately say that the answer is no. Otherwise, we know that both prefixes are sets of the same size, and there aren't many possible sizes. So what if for each size, up to smallest of two final sizes, so for each size, let's try to answer the question if corresponding sets, the first k different elements in A and first k different elements in B are equal or not. This can be done in multiple ways. One way is to, every time a size of a set increases, it means that we get a new element. So we can record new elements and then repeatedly add new elements. That is like k's new element in A, k's new or i's new element in B. And we can add it to a symmetrical difference of the sets. So if some value is already there, it means it was added from A and now it gets added to B, so we remove. Otherwise, we insert. And the sets are different if and only if the size of their symmetrical difference is non-zero. So that's one way. This is the intended way. Now, another possible way is, remember how I said that a size is the most simple hash function? Well, there is another, also reasonably simple hash function. That is, for each, let's just compute XOR of the set. If you do it the straightforward way, then you probably will end up with collisions. For example, sets 1, 2 on one hand and just 3 on the other hand clearly have the same XOR. So instead, each value in A and B is going to be replaced with a random 64-bit number. The only condition we have is that we don't count duplicates, that's first, and second, the same number in A and B should be replaced with the same random number. Then you can use just XORs of the sets to quickly tell if sets are equal or not. This is actually a solution by some other smart people. How do you... What is his name? Like so. Yes, okay. This is a solution by one of the smarter guys on AtCoder. You can see that we use hash. Hash is just a random number. And this mapping here just remembers if we already assigned some random numbers and we have to use the same number. And then you can compute prefix XORs, and that's it. And you can compare prefix XORs afterwards. That is a cool way of solving some set equality problems. Obviously, it wasn't intended, but whatever. It's cool. Now, there's a very dumb way of solving this problem, which is what I did. So because of how you have like queries, there is one popular method of answering queries, which is Moss algorithm. Mo works in O of n square root of n. And for Mo, you need to be able to efficiently move x one to the left and y one to the left, one to the right. yes, both endpoints of your interval, you should be able to move one to the left, one to the right. So that's then if you sort queries appropriately, that is grouped by block, and then, well, okay, I'm gonna tell you what. If you know Moss algorithm, then you should understand how it works. Otherwise, it's probably not necessary to learn it now. Although I do remember that one of the G problems recently, or not that recently, last year, required Moss algorithm in ABC. So it was like the first thing that I thought of after hashing, but I decided that hashing is kind of unfair. So I decided to implement something deterministic. So I came up with Moss algorithm. For more, you need a way to move both endpoints and then maintain some information so that you are able to answer queries in all of one time. So I once again maintain symmetrical difference of two sets. And I also maintain how many times each number appears in A and how many times each number appears in B. So both of these are easily updatable. Then knowing the entire mapping, you can easily keep track of size of symmetrical difference. So that's what I do. And the answer is yes if difference is 0. So yeah. It took some optimization to squeeze it, because if you just use a map here, it will be O of n square root of n log n, which is not great. So I used a fast hash table from policy-based data structures. So that's one way to squeeze certain problems, certain query problems. If you don't know what to do, you can always do more. You risk ending up in a O of n square root of n log of n not passing, but generally log n is avoidable in such problems. But even then, like, this solution works in roughly half the time limit, so it's not super safe. For example, if you pick a wrong block size, then you may end up having trouble. But I decided to discuss it either way because I think it's fun. Next problem F, 1/4. We have a convex n-gon. We want to draw one diagonal of this n-gon in such a way that it cuts roughly a quarter of the n-gon off. So our division should be as close to 1/4 and 3/4 as possible. For this problem, you may notice that if we, instead of drawing a diagonal, we pick some vertex and we draw imaginary line that does not need to be diagonal, but it must pass through this vertex. And there is exactly two such lines that cut 1/4 off the n-gon of the polygon. But for the sake of simplicity, we may consider the one that goes like to the right, or counterclockwise is probably the better term here. So obviously the closest division we can get in terms of diagonals will be the one, like the first vertex before this non-diagonal cuts are sync, and the first vertex after. I should be able to do some painting. Because it's geometry, it may be best to actually do some painting. So what I'm saying is, consider this vertex. Roughly a quarter of this will be like so. So this is 1/4 exactly, right? But this is not a diagonal. It doesn't pass through the other vertex. So we will consider this vertex and this vertex as they are the closest. Now after that, let's move to the next vertex. Once again, draw imaginary line. Once again, consider next vertices and previous vertices. Move once again, draw a new imaginary line, consider previous and next. You see that previous and next, they move the same way as the vertex moves. So you move clockwise, they also move clockwise. So we may keep track of both of them just by like 2 pointers. So this is what I did. So obviously we need a way of telling the area of a triangle, because each move, increasing either of the pointers or decreasing corresponds to adding or removing one triangle. So this is what I do. First I compute the entire area, then I grab myself like what do I want to be, what is my target. Then I have 2 pointers left and right, and I keep track of area between left and right. I try increasing right for as long as it makes sense until the area of our piece gets too big, basically. So I try increasing this area by moving right from right to next right, which is basically right plus 1. So this adds this triangle. Then I just move right. And for the sake of being safe, I take minimum with answer all the time. I actually wonder if you can remove it here. Probably not, because then you will just compute minimum over parts b that are strictly greater than 1/4, which is not necessarily the case. And then once I'm done moving right, when my piece got too big, then I have to move left. And then I just move left, I remove that piece. I move left from left to left plus 1, so it's the same as removing this piece. So I decrement the area, and that's it. So I keep, 2 pointers. If you are familiar with that technique and familiar with some basic geometries, then you should understand this problem. Next problem is actually for geniuses, which I'm not. So we are trading some stocks for the n days. We got price. On each day we can buy, sell, do nothing, and we want to find maximum profit that is affordable, that is available. No conditions like you may engage only in one transaction at a time, etc. Nothing like that. So this is actually very smart. I was thinking of something like convex hull trick or Lee Chow tree actually, but it's too complicated. In this problem, there is a very beautiful solution. So for the case when you cannot engage in multiple transactions at a time, there is a simple solution when you maintain your prices, and at each day, like your prices at the previous days, and each day you take the cheapest price in the past. And if it makes sense, if profit of the following transaction is non-negative, then perform this transaction. The transaction is buy at the cheapest point in the past that you haven't bought on and sell today. So iterator or the referenced iterator is the cheapest price before that moment. If it makes sense to buy then and sell now, then do it and remove this price. However, if you happen to be in this case, like you already sold something on day I, you may later use this price that we inserted to buy something on day I retrospectively. So then your overall action will be like you kind of sold and bought on the same day, which is clearly equivalent to doing nothing. So that's why that solution works for the modified version of the problem. However, it also means that our strategy is non-optimal for this problem. If you consider prices like 1, 2, 3, 4, then this solution will print 3, whether the actual answer is 4. You buy 1 and 2 and sell 3 and 4 for the profit of 7 minus 3 equal 4. So it happens because if we ever sell on a given day, there is no way for us to then actually buy stock on this day. Even if we use this later, it will mean no action. So we need to add certain way to actually buy stock on that day, if there will be many high prices in the future. So we fix this by simply adding another instance of PI. So then using one instance of PI will correspond to doing nothing, and using both instances of PI will correspond to actually buying more stock on this day, to holding to 2 stocks simultaneously. So the formal proof of this solution goes along the lines of actually optimizing dynamic programming when you, for day I and J stocks, you compute what is the maximum profit you can get if on day I you want to hold J stocks. There are simple transitions to this problem, to this dynamic programming. They result in intersecting convex sinks, which is actually what I've been thinking during the contest. If you go to the editorial of this problem, you will see, yeah, I did exactly that. I did this dynamic programming that is described here. And I went to these convex sinks, and then I thought maybe we can intersect them somehow, but it wasn't going to happen. I had so little time left to even investigate it. But these things can be used to prove that this solution is actually optimal. It's kind of intuitive if you think about it, because we always pair transaction with the cheapest price in the past that we could have possibly used. But we always pair it with the cheapest price in the past. So that kind of makes sense. But if you want to prove it mathematically, then you have to consider that dynamic programming. In problem H, we had an undirected weighted graph, and some of points were special. First k points were special, and we needed to solve several queries. So we were given 2 special points, and we wanted to check if we can travel from one special point to another with a certain condition. Namely, condition was we cannot spend, we can move only from special houses to special houses. We can use roads that go to other houses, but we cannot stay in those houses, in those vertices. So we can only stay in special points, and each ti units of time we have to stay somewhere. So we needed to find a sequence of special houses. Each 2 consecutive houses in this path needed to be at most ti away from each other. So yeah, we needed to answer are the points connected in the corresponding special graph. So what I noticed is obviously as t increases, the connectivity improves because we can spend more and more time outside of special vertices. So what I've been thinking during the contest is let me create a disjoint set union to keep track of connected components among the special houses. Unfortunately, I cannot afford to use all edges. I cannot compute all distances between all pairs of special points. But if I was able to, and for each special pair I can compute distance, let's assume I computed some distance, then I can insert the corresponding edge into disjoint set union, merge corresponding connected components, and because t are increasing, I will gradually increase t, and insert all edges with distance less than or equal to current t, and then query this joint set union for connectivity. So obviously this was too hard because the number of edges is k-squared. Also, I needed to somehow compute k-squared distances, so that was not going to happen. I started thinking about minimum spanning tree, and there is a solution that uses spanning tree, but we will not cover it here. You can read it in the editorial if you want to. There is actually a better solution to this problem, that instead of generating all edges explicitly, all k-square edges, it tries to use the original edges, original m edges. If I can find it. Wait, I clicked on the wrong submission, I'm sorry. So it uses original edges, but it modifies the length of each edge as original length plus distance of A and distance of B. A and B being the endpoints of this edge, and distance being the shortest distance to a special point. These, of course, can be computed by using multi-source Dijkstra. When we add all distances of all special points to 0, and then you just perform your usual Dijkstra. There is nothing complicated about multi-source Dijkstra. So yeah, modifying distances of each edge in such a way, it is quite clever. Better way to write this would be distance A plus C plus distance B, because then you can clearly see a path from one special point to another. Unfortunately, I was not able to think about this in contest, but you can easily prove that it works. First of all, you will need to prove that if we change weights in this way, endpoints were connected, then they stay connected. If they weren't connected, then they remain unconnected. But it is not hard. Because each pass, like for each pass, we can select one representative edge, and this edge will be counted at some point. Like each such edge, it counts all optimal passes that go through this edge. So yeah, it's actually very clever thing when you can change the weights or distances in tree in some way, or a graph, because this is actually not a tree. So yeah, that was the contest, and I used AtCoder library for this joint set union because it's kind of lazy at this point. So yeah, thanks everyone for watching, and I'll see you tomorrow with a tutorial on bipartite matching. Bye bye guys, see you soon.